Here we see the initial velocity of two spheres that are going to collide obliquely. For convenience, we take the line joining the centers of the colliding spheres to be the x-axis. Now I'm showing the origin of the coordinate system at the center of sphere A when it collides with sphere B, but of course we could put the origin here. The main point is that the x-axis is along the line joining the centers of the spheres while the spheres are colliding. Of course the collision time is a tiny fraction of a second. Now of course the spheres don't have to collide in this manner. We could imagine the spheres colliding like this. In that case our x-axis would be along here and this would be our y-axis, say. But just we can always orientate the picture so that when the spheres collide, the line joining the centers is a horizontal line. And we can refer all the velocities in the picture to this xy coordinate system. Now just like in previous videos, we assume that no external forces act on the system. By system I mean the two spheres. So the resultant external force on sphere A is 0 and the resultant external force on sphere B is 0 before, during and after the collision. So the easiest way to visualize this is to visualize two spheres in outer space, far away from any gravitational field, and they're moving with these initial velocities UA and UB. If no external forces are acting, they will continue moving with these velocities forever until of course they collide. Alternatively, we could imagine that the two spheres are resting on a horizontal table and we have a plan view. So we could imagine looking down on, say, two pool balls or two snooker balls. But these balls are on a perfectly smooth table. So if we take, say, an edge-on view of this ball, okay, this horizontal line is the pool table. Well, in this case we do have external forces on each sphere. We have the weight, which is vertically down, of course, but that's counterbalanced by an equal but opposite contact force, a normal reaction. So if we add these two vectors together, we get 0. Also, we're assuming that the table is perfectly smooth, so that we don't have any friction force. So as I've said several times before, this ball just slips along the table, so this point always remains in contact with the table. So, the net or resultant external force is 0. Now, like in a previous video when we looked at the conservation of momentum for the direct collision of two spheres, I will do a quick derivation of the conservation of momentum for this oblique collision of two spheres. So, no external forces act on the system. The only time we have a force on each sphere is when the spheres collide. Now, the force on each sphere doesn't have to be constant, as I've explained before. So you could think of FAB as the average force on sphere A due to B, and FBA is the average force on sphere B due to sphere A. By Newton's third law, these average forces are equal in magnitude but opposite in direction. And that's true regardless of how each sphere is moving, how fast each sphere is moving, or how big each sphere is. One sphere could be much more massive than the other sphere, for example. I've drawn these two spheres to have identical sizes, but their masses could be very different. Now we can apply Newton's second law. So the resultant average force on sphere A is FAB, and that's equal to the mass of sphere A times the average acceleration of sphere A. And we have a similar situation for the force on sphere B. Now, to get the average acceleration of sphere A, we have to take the velocity of sphere A immediately after the collision, which is VA, shown here, subtract the velocity immediately before the collision, which is UA. Okay, so the acceleration is the change in the velocity divided by the time taken. So t here would be the time of the collision. So typically we're talking about a time of maybe a few hundred microseconds, a few hundred millionths of a second. So you can see that calculating the average acceleration for the case of an oblique collision is a bit more complicated, because VA and UA are vectors that are not along the same line. So let's see how we would calculate using a picture vector VA minus vector UA. Well, I'll just draw UA over here so I can move it parallel to itself, of course, and I'll draw VA's tail at UA's tail. Now I have to actually exaggerate this, because when we subtract we must get the change in the velocity. Okay, so you can actually see from the picture that VA here is not quite accurate, because when we work out VA minus UA we must get a vector that's horizontal. So VA would actually need to be a bit longer than what's shown in this picture here. Or perhaps the angle should be different. Okay, so I'll highlight this vector. So this is vector VA minus UA. You can see that from the triangle law. If you add vector UA onto vector VA minus UA, you will get vector VA. Why is it in the same direction as the average force on sphere A? Well, the average force on sphere A is just a scalar multiple of the average acceleration. So the average acceleration of sphere A is in the same direction as the average force. It's just a vector scaled up by the mass of sphere A. And the average acceleration is in the same direction as the change in velocity, because the t is just a scalar. T is just a number. Now the t on both sides is the time for the collision. It's obviously the same, so we can multiply both sides by t. The next thing we do then is just multiply out both sides and bring all the terms involving the initial velocities to the left, so that's the u's, and the terms involving v's are brought to the right. So you can see the left hand side is just the total momentum of the two spheres before the collision, and the right hand side is the total momentum after the collision. Now let's consider the y and x components of the velocity vectors. So I'm going to call the x component of vector UA UAX and the y component UAY. Similarly for the velocity UB and the final velocities VB and VA. Now let's go back to the equation showing the conservation of total momentum. So we can write the momentum of sphere A before the collision like this here. So the momentum of sphere A before the collision is in the direction of the velocity. You know, we just multiply the initial velocity of A by this scalar, just we scale it by the mass. So momentum is a vector quantity. It's pointing in this direction. But you know, when we break the velocity vector into its two components, we can write vector UA as the sum of its two components. We just, by the triangle law, we just sum the x and y components. Next we will show that UAY, the y component of the initial velocity of sphere A, is equal to VAY, the y component of the final velocity of sphere A. And we'll do the same, of course, for sphere B. We'll show that the y component of the initial velocity of sphere B is equal to the y component of the final velocity of sphere B. So we'll be able to cancel out these terms on both sides. So we'll just have a momentum equation involving the momenta in the x direction. So on this diagram we're going to show that this vector here is equal to this vector here. Okay, so the vertical components don't change, and similarly this equals this. Now we did this kind of thing in a previous video actually, where we looked at a single particle colliding with a wall. So we showed that the y component of its velocity didn't change, but the x component obviously did change because there's a force on the particle in the x direction. So we'll run through that argument again for this situation, so it's going to look almost identical. So the first thing we notice is that the force on A due to B is entirely in the x direction. So we could write the force vector like this: FAB, that's without the arrow, is the magnitude of the force, and we multiply it by unit vector I. Okay, that's the unit vector lying along the x direction. By the way, you can see that FAB is going to be a negative vector. Okay, because FAB is pointing to left. So this number FAB is some negative number, and we multiply by unit vector I. There's no j component. We could put in 0j if we like. Okay, we've set things up so that there's no j component to these force vectors. So if the average force is entirely in the I or x direction, well, it's obvious that the average acceleration is going to be entirely in the x or I direction. So there's going to be no j component to the average acceleration. So we can write the acceleration of sphere A as A sub A times I. So where this quantity here is a positive or negative number. So now all you need to do is fill in for VA and UA. So you write VA as a sum of its x and y components, VAX plus VAY, and you do the same for UA. Write it in terms of its x and y components, but this time I'm using the I and j vectors. It just makes it really clear that what we're trying to show. Since there's no j component here, you can see that these j components must cancel out. So if they cancel out, they must be equal to each other. So VAY must equal UAY. Okay, you can see the minus sign in here. If I took in them, I suppose it's probably fairly obvious, but just to make sure if I take in the minus sign here, we get this vector in here, and we just gather up the I terms, and we gather up the j terms, but the j terms must give us 0. So VAYJ minus UAYJ must equal 0, from which we conclude that VAY equals UAY. Of course, we can use the exact same argument by looking at the average force on sphere B and concluding that VBY equals UBY. These two vectors don't change. So now we see that because we can cancel these out on both sides, on the left hand side we end up with the momentum in the x direction before the collision. Or if you like, this vector here is the x component of the momentum of sphere A before the collision, and this component here is the x component of the momentum of sphere B before the collision. So if we add these together, we get the total momentum. We get the x component of the total momentum of the spheres before the collision, and similarly on the right hand side we get the x component of the total momentum of the spheres after the collision. So this is a key formula that we will use to find the x components of the velocities of the spheres after the collision. So you see, we will be looking at the x components of the initial velocities before the collision. Of course, if we know what the masses ma and mb are, and we know what the x components of the initial velocities are, we still have two unknowns here. So our second equation involves Newton's law of elasticity. So that tells us that the recession velocity of the two spheres in the x direction after the collision is minus e times the approaching velocity of the two spheres in the x direction. So it's important to note that we are only considering the x direction. That's the direction in which the collision happens. And now as for the y direction, just to recap this, we saw that the velocities in the y direction do not change for sphere A and for sphere B. Okay, to get the recession velocity of the spheres in the x direction, we get the relative velocity of one sphere to another sphere. So we could get, say, VAB. We could also get VBA. The only difference between VAB and VBA is a sign change. Okay, so I'll just work with VAB. So this is the velocity of sphere A relative to sphere B after the collision. And we just want the x component of that velocity. So if we use VAB on the left hand side, we have to use UAB on the right hand side. And we want the x component of sphere A relative to B before the collision. Now E, the coefficient of restitution, depends on the materials that the spheres are made out of. We know that that's a number between 0 and 1. So we've seen this before. Okay, so what's VAB? Well, the velocity of A relative to B is just VA minus VB. That's from relative velocity. But we want the x component of this. Well, the x component of VA minus VB is got by getting the x component of VA and subtracting the x component of VB. So similarly here, we have the x component of UA minus the x component of UB. So highlighted are the three facts that we need to solve oblique collision problems. We need to note that the momentum in the x direction is conserved, where the x direction is the direction along a line joining the centers of the two spheres when they collide. We need to know that the y components of the velocities of the two spheres don't change. So the y component before is equal to the y component after for each sphere. So the y component is perpendicular to the x-axis, perpendicular to the line joining the centers of the two spheres. And finally, we have Newton's law of elasticity, but applied in the x direction. Now let's plug in some numbers by taking this particular example. Let's suppose that E is 1. In that case, we have what's called an elastic collision. So the kinetic energy before equals the kinetic energy after. No loss in kinetic energy. So as we said, in reality this doesn't happen. E is always less than 1, but we can imagine E is so close to 1 that we can take it equal to 1. Now here are the initial velocities of the spheres before the collision. By the way, we need to know the masses of the two spheres, MA and MB. So let's assume that for this first example the spheres are identical, which means that they have the same mass. Let's call that mass M. Okay, so let's start with momentum conservation. So the mass of sphere A is M. The initial velocity of sphere A in the x direction is up here. We can see that it's I. So I can just write I here. The mass of sphere B is also M, because it's identical to sphere A. The initial velocity of sphere B in the x direction is minus I. Okay, so we see we get the total momentum before the collision is actually 0, and that's quite easy to see from the symmetry of the situation. The two spheres have the same mass, and they both have the same speed. You know, if you get the magnitude of this vector, you get the square root of 2. Root 1 squared plus 1 squared. And it's the same here for the magnitude of this vector. This is root 2. And also by the directions, you know, this angle is actually 45 degrees. Because this is 1 over 1, inverse tan 1 over 1. And the same goes for this angle here. So by symmetry you can see that the x component of the momenta will cancel out. Okay, so that's no surprise. Also we can divide across by m. So m doesn't actually come into it, so the mass of the spheres is not a factor in this problem whatsoever. So regardless of the mass of the spheres, we're going to get the same answers for the final velocities of the spheres. Now let's apply Newton's law of elasticity So VAX minus VBX. Now you don't have to keep putting in the x's. Once it's understood that we're talking about the x direction, you know, you could leave off these subscripts if you like, but I'll just leave them in just to make it clear. E is 1. Now UAX, well, we already had that. There's UAX and there's UBX. So it's I minus I. That's I plus I. So now we have our two equations and two unknowns. So we have to solve between these to find out VAX and VBX. Now these are very easy to solve, so I'll add VA plus VBX onto VAX minus VBX. So not the VAs but the VBs will cancel. So we VAX plus VAX, that's 2 VAX equals 0 minus 2i. So that's clear, I don't want to dwell too long on that. So VAX is minus I. So if VAX is minus I, if this term is minus I, then VBX must be plus I, you know, when we solve this equation for VBX. So now we can write down the final velocities of the spheres. We have the x components. So to get the velocity of sphere A, we want its x component, which is minus A, and we want to add that minus I, sorry, and we want to add that onto its y component. That would be VAY. But this is where we use the fact that UAY is the same as VAY, because there's no force in the y direction, no change of velocity in the y direction. So here is sphere A, its velocity in the y direction is j. So that's before the collision, and after the collision it's also j. Now let's get the velocity of sphere B. Well, its x component we just found out is I, and we have to add on its y component. But its y component after the collision is the same as its y component before the collision. So its y component before the collision is j. So its y component after is j. So there we have it. We found the velocities of the two spheres after the collision. By the way, it's assumed, of course, that these two spheres will collide. You know, the starting positions of these two spheres could have been totally different. The velocities that we give them will remain constant until they collide, of course. I mean, if they don't collide, they'll keep moving with these velocities. But you know, it's assumed that these two spheres are positioned in such a way that when we give them these two velocities, that they will actually collide. Now in this case you can see a symmetry in the velocities of sphere A and sphere B. A symmetry along this line here. A symmetry about this line. So notice the symmetry in the initial velocities. The speeds are the same, both root 2, and the velocities make an angle of 45 degrees with the horizontal, albeit in you know, this with the positive x-axis and this with the negative x-axis, but it's the same angle of 45 degrees. So the spheres do collide, you know, provided that they're at the same distance below the x-axis here. You can see the symmetry in the velocities after the collision also. Notice that the angle of rebound, in this case 45 degrees, is the same as this angle here, 45 degrees. That's because we have an elastic collision, E is 1, and also because the spheres are identical, both masses are the same. In general, the angle of reflection will be something like this. This angle will be greater than this angle of incidence. Usually what happens is the x component of the velocity decreases. Now in this case the x component stayed the same. Well, it stayed the same in magnitude. You see it's minus I here. So the magnitude of this vector is 1. And here the x component of the initial velocity has magnitude 1 also. The x component is plus I here. They're the same because it's elastic and the masses are the same. In general, the x component will decrease. So in general, you might have an x component that looks like this, but the y component stays the same. Okay. So the y component stays the same, the x component decreases. So that means that this angle will usually be greater than the angle of incidence, where the angle of incidence is just this angle here.